Thanks everybody for coming. I really appreciate it that you're going to hear my ramblings for a little while here. So this talk was basically born out of the fact that I've been speaking to a lot of people about data science and oil and gas over the last 2 or 3 years. And I honestly have no idea what I'm doing. And it's a complicated world. And so I kind of put this together just so that I could sleep at night when I'm actually trying to do my data science stuff. One thing that has happened, though, is that I've given this talk a few times, then everybody goes, oh, that's a great talk, but what are you really doing? And so, you know what? I just cobbled this together. This is a little project tracker I have for my team at work. And if you can just see on the left-hand side, those are some of the projects we're working on. Some of them I can't talk about, but generally, a lot of it is just automation stuff. We have folks that are doing a lot of work, pushing things into Excel, pushing things out of Excel. And we're just trying to work basically at this stage at the bottom of the data science needs pyramid, getting stuff collected and automated so that people have more time to do the more valuable work. And just as an example, somewhere in the middle there, we have one called geophysical log standardization, in which my team is taking different well logs, cutting them up, splicing them up, doing a few things, bits and pieces. And the geophys said, well, that's so cool. Let's try this and let's try that. And now it looks like we're going to build a predictive model for some other work. It's like, you kind of have to go through that journey no matter what. So we are doing a lot of stuff, and I can talk to you offline about these kinds of things. But otherwise, my boss said I can't talk about Synovus stuff. Otherwise, I have to get lawyers involved, and I don't want to have to get lawyers involved. So this talk is mostly a thought experiment, and based on things like this. So this is Andrew Ng. I'm sure most of you know who he is. And he said, or he keeps saying over and over again, AI is the new electricity. I was looking at that and going, oh boy, that just sounds like a lot of hype. Like, what on earth is he trying to say here? But he's a smart guy, so obviously he must mean something by it. And hopefully I'll kind of convince you as we go on that this is not a hyperbolic statement. This actually is quite meaningful. And we'll talk about electrification. But really, when I start talking to folks about data science, this is usually what it comes down to. It's like, what tool should I use? Should I use AWS? Should I use Azure? Should I use R? Should I use Python? If you want those questions answered, go talk to Khaled, okay? Because he knows what the industry wants. This is all going to change in 2 minutes, okay? That's the issue with all this. And in the end, it ends up looking like a big alphabet soup of terms. And I don't want to talk to you about tools. I want to talk to you about the greater picture, about what data science really means within context. And so as a data scientist, generally you try to find data, and then you try to fit that, train up that data so you can come to a result. And so in trying to understand what data science means, it's very confusing, as we all know currently, I thought I'd look back into the past and use different technological trends and technological transformations and try to identify trends that come out of that we can apply to our current state. So that's basically the elevator pitch for this talk. Okay, so let's go to the past. And Mark Twain said history doesn't repeat itself, but often it does rhyme, and that's true. You'll see that trend as we go through history here. So this is broken up into 2 parts. Part 1, we'll talk about the past, and then we're going to have a little mini hackathon in the middle. Then I'll talk about the present state a little bit in the future. Okay, so Tim was showing a few examples of some of these technological transformations that I'll talk about. The first one is the Jacquard Loom. We're going back here, folks, to 1803. And you'll see how some of the problem solving and automation things came out of something as simple as a loom, things that we talk about in data science all the time. We talk about electricity, and that's what Andrew Ng was talking about. That kind of delves into the whole tools issue. What tools should I be using for data science? Well, that was an issue in electrification as well. And adoption, that's also an issue. And we'll talk about computing, actually computing way back into 1632, and what hype looks like and the confusion that results from technological transformation. So I'm trying to show to you that data science has issues with all of these things right now, but we're right in the middle of it. So it's very challenging to understand what that looks like, but we can look to the past to see how this might play itself out. Okay, so the Jacquard Loom. Basically, before 1803, if you wanted to build a tapestry, it took you about a day to build an inch worth of tapestry. So it took a very, very long time. Until Jacquard in France came up with this brilliant idea. I still don't know how on earth he came about with this. But basically, it uses a series of punch cards in order to program the loom to develop a different pattern on your tapestry. And as a result, that would take you, basically in a day you could build 2 feet worth of tapestry as opposed to 1 inch. And like, I mean, that's a classic case of automation here, and analog automation, but that's a pretty big leap. So I'd be very afraid if I was a tapestry or weaver at this time, right? This is what tech does. It always automates things and then roles just switch around a little bit. This is kind of funny too, because actually this was the inspiration for Charles Babbage, who is basically the godfather of computing. He got the idea about computing from this loom. So it's kind of interesting how things feed upon themselves. Okay, so now we'll get on to electrification, and this one is really fascinating to me because we just take it for granted. We have electricity everywhere, but before it was around, I mean, it was a big deal to have light. I mean, I've read stuff where if you wanted to generate 1 hour of light using wood, it would take you 12 hours of work. And so now we've obviously shrunk it down so that it's meaningless, but when electricity first came in, it was basically I think the International Society of Engineers called it the greatest engineering achievement of the 20th century. And I think it's so widespread, so ubiquitous that we take it for granted, but it is truly an achievement. This was one of the first electrification projects in France, in Paris in 1878. And this is what spurred Edison on to electrify the United States. So, okay, well, obviously electrification, it's an obvious thing. We all benefit from it. We get lights, it's wonderful. We get heat if you're from certain parts of the country. So wouldn't this be an obvious thing that everybody would want? Well, it wasn't an obvious thing. It took a very long time to come about. There were the War of the Currents that some of you may know about, where Edison versus Tesla / Westinghouse. Tesla loved direct current. You could maybe call that R. Tesla loved alternating current. You could maybe call that R. Edison loved direct current. You could maybe call that Python. Tools again. You had all kinds of wild and wacky systems out there. Like in Berlin, you had a 10,000 volt arc lamp system that was set up. So if you even got near that, you'd be fried. You had 500 volt street cars everywhere. Like everything was available out there. It was just a complete mess of tools and standards. Till finally that kind of settled itself down. Alternating current finally went out, but it took legislation to actually kind of get that into place. The War of the Currents was so bad at one point that Edison actually sponsored the electric chair to prove how evil alternating current was, because it could fry you quite quickly. And even in North America, it took almost 50 years before it was adopted widespread throughout the country. And now we just take it for granted. So it's a big deal. But it was not an obvious thing. Looking back now, it's like, oh yeah, of course we have it everywhere. But it was quite an effort to get it in place. Okay, so computing. There's maybe a little more relevant to a lot of us in terms of how this might look. But I'm going to take you back a little bit further yet. So computing, I would say, started even, we all think of digital computers. We'll get to that in just a moment. But computing, as an example, logarithmic tables were basically started coming about in the early 1600s for navigation and engineering. And for those of you who aren't in those fields, basically logarithms transform problems of multiplication into problems of addition and subtraction. So it makes life a lot easier if you're doing calculations on a ship to understand where you're going. The issue with these things is that they took very long time to build. And so the graphic on the right-hand side here, like I said, took I think it was something like 25 years to calculate the first 14 places. And it was done laboriously by hand to figure it out using a finite difference method. And it took till 1952 to get all numbers, I think from 0 to 30,000 to 20 places. And now, of course, you can just pop that up on your iPhone and get it to 15 places immediately. So I'm sure most of us don't want to go back there, right? Okay, so that's great. Well, we don't have to worry about that. But back in the 1950s, these are what computers actually looked like. It was a job, it was not a thing, it was a profession. And this is actually at NASA, in which people were developing wind tunnel experiments in this case. And these are the people that used those logarithmic tables. And so it took a lot of effort to kind of do all the calculations. And then you had these people with redundancies to basically figure out if the calculations were done properly, because if they weren't, it was very dangerous. If you've seen the movie or read the book Hidden Figures, that's basically the story of those folks and how a lot of them pivoted into different roles afterwards. So just as a nice aside, I love this. This is how tapestry weaving kind of cycled back into the digital age. With the Apollo guidance computer that was basically installed on the Apollo modules. It's the 50th anniversary of the Apollo moon landing, so I've been reading up all about this. This is the actual memory bank of the Apollo guidance computer. It was not a chip, it was actually wires that were all threaded together by two weavers, and it would take them 8 weeks to put this all together. And so it's kind of funny where like a very, very old school skill kind of came back in terms of building what was probably, still is probably one of the best designed computers ever. It was one of the few computers that has executive function, which it could decide, if you would give it 3 tasks, it would decide which one was the most important. And if it was having issues with that, it could actually reboot itself and restart all over again. It had 32K of memory, and it was something like 0.04 megahertz. So, but it was brilliantly designed, absolutely brilliantly designed.
I just wanted to point out this is the origins of the term hard core, because those are cores.
Yeah, exactly right. Yeah, absolutely. And it was actually a brilliant system too, because you couldn't fry this memory. And it actually happened at one point where they had an electrical outage, but this lasted because it was all hard coded. Exactly. Okay, so why am I talking about this? Well, before this time, computing was thought of as this flaky, weird thing with vacuum tubes, and literally the term bugging came in because somebody found a mosquito or a fly. Yeah, Grace Hopper, exactly. Inside one of the vacuum tubes. And so they were considered very flaky and unreliable. But then once this machine was built and came out, then the computing age basically started. And people thought, wow, you can do anything with a computer. If you can go to the moon, you can do anything. So what happened out of that? Well, computing all of a sudden just blossomed. At least the investment blossomed. So computing capacity increased over 100-fold in the 70s and 80s. And every company thought, well, hey, if we can send a person to the moon, we should get a computer, and this will revolutionize our business. It'll be incredible. And so there was a lot of money that was invested in that. But in the mid-80s or so, Robert Solow, who is a Nobel Prize economist, said, hey, well, you can see the computer age everywhere, but in productivity statistics, nothing has changed. So people aren't doing any better with computers around. What's happened here? And so we'll discuss that right here. So this is basically, I have to have a graph, right, data scientist. And so this is a graph of GDP per hour worked in both the United States and Canada. And you can kind of see that, yeah, for the most part, right until about the mid-90s, there was no real change. We start off in 1970 before widespread adoption of computers, and we go right through to the mid-90s for about 25 years. Nothing had really changed. It took a long, long time to figure out how computers would fit into our world. It was not an obvious thing. Just because you can send a person to the moon doesn't mean that you can implement a computer and it will automatically change your world. Does that sound a little bit like machine learning and AI right now, right? It's the same idea. So it took right till about the 90s before they think that things finally changed. We solved the productivity paradox. We figured out what computers were actually useful for. And some people actually still argue we still haven't really quite figured all that out yet. So just kind of a little cautionary tale there. So what happened? Well, I think there's also the impact that it's hard to measure the impact of computing. Now, obviously, it's in our phones, it's everywhere, it's just part of our lives. But from a day-to-day measure, how do we know how they've impacted things? In a lot of ways, I mean, when you look at your email box, it's probably a step back in terms of your productivity, right? I think another thing that came out was also that investment isn't created equal. I was reading a few articles about when they introduced word processing in the 70s. You know, it's like, okay, well, obviously, you know, a typewriter is very inefficient, and if you make mistakes, you erase it. But the level of effort that was brought in to automate word processing probably was not worthwhile, because those systems were very slow, very clunky, and they were just as problematic as the typewriter, but at least the typewriter was just much easier to fix. Same thing in manufacturing. Actually we were talking a bit about control systems here earlier. A lot of the control systems that were in place in manufacturing processes were already analog, and they were working quite well. So putting a computer in there sped it up a bit, but probably wasn't worth the investment. However, eventually, some business models did change, and they did make a big difference. One of my favorite examples from a former industry I was part of was American Airlines, and when they developed the Sabre system, which was an automated booking system that allowed you access to all seats on planes, that just opened up the aviation industry, because then you could see what the other airlines were doing. You could book flights all over the place. And American Airlines, I mean, I think they were kind of the harbinger of Google here, where they basically gamed their algorithm so that you would gain access to their seats first before anybody else, and that was a huge game changer for them. Also, the oil and gas industry, I'll give a plug to my training here as a geophysicist. The general thought that when 3D seismic came into play in the early 80s and into the 90s, that basically cratered the oil price, because we found so much oil based on that single technology, and that was only available through computing. There's no way you could do that by hand. Well, Volo might be able to, but I can't. So it takes time to figure out what these technologies will be able to do for you. Okay, so in the end, for part one, so what does the past tell us? We often think that technology is a very linear thing. It's like this builds upon this, builds upon this, builds upon this. And yeah, looking back, it certainly looks like it does. But no matter what, we're still people, and we still react to things in the same way over and over again. So when we see new things coming, we tend to get a little bit resistant. It's hard to understand. Some people jump on it, some people don't. And so we have that kind of same circular reaction to things. And I think that's kind of where data science is right now. And I'll talk about that in the second part. So, okay, so we trained our data set. Now let's predict, which is what this part is all about. I love this quote because a lot of people feel put upon that, okay, my job might disappear. Well, you know what? Jobs have been disappearing for a long, long time, and new jobs have started appearing. It's more incumbent, I'm sorry to say it, but it's more incumbent on you to figure out how you fit into this new world than feeling like a victim. It's just the way the world is working. I'm scared to death for my 10 and 11-year-old. I don't know what to tell them. If they went up to me and said, right now I want to do this, I said, I don't know how you're going to get there, but it's passion that'll get you there. And so that's what we need in a different stage in our lives, right? So let's look into the future. All right, so what's the present state of data science? This little doodly graph here is called the Gartner hype curve. If you haven't heard of Gartner, you should look into it, because your decision makers, anybody who will be interviewing you or your current bosses, know about Gartner. They're a management consultant company who basically tell companies how you should function. And so they have this little hype curve that they use for any number of technologies. And they seem to think that it follows this general trend. There's a bit of debate about that, but it does serve a few functions here. Basically, a tech will come out. It's all very exciting. And the visibility, on the x-axis is time, on the y-axis is visibility. So initially, right away, somebody sees something like blockchain and goes, wow, this is super cool. Look at all the awesome things you can do with it. And then it goes up to this peak of inflated expectations where this can do everything. Then you start doing things, and it's like, oh, wait, it doesn't work quite as well as I expected. And it doesn't do anything at all. What's wrong with this? Because we thought it could do everything. And so that's that typical trough of disillusionment. And eventually, just like we saw with computing, people figure out what it really does well, and then it kind of ends up being at this plateau of productivity. And so I think this is kind of an insightful little graph. And you could argue that data science is anywhere along this curve, depending on what your experiences are and what industry you're in. In oil and gas, I'm sure it's right around that peak, but in some companies it's kind of going into the trough so far. But in other industries it's very different. Like I said, computing took a long time to find its stride. Data science is no different. But the difference why data matters is that it is everywhere. And this is a bit trite, but it is true. It's amazing. We're collecting data on everything we do. My heart rate is being measured right now. My steps are being measured right now. And that seems trivial, but it's not, because there's business models in there. You can make money off this stuff. It's challenging. We may not have it all figured out, but in 5 or 10 years, it'll become obvious looking back. And so this is the exciting time to understand this. We're measuring literally everything. Like I was reading an article, actually came out in CBC a month ago or so, where all the auto manufacturers are monitoring your habits in the car, everything that you do, everywhere you go, what radio stations you're listening to, and they're monetizing that. And the agreement for you to say that that's okay is basically when you turn on the car and hit okay for the privacy statement. Basically, you're arguing that yes, it's okay for me to, for the car company to sell all or collect all that data and sell it. That hasn't been discussed, but they're monetizing that, right? So it's everywhere. Get used to it. And another trite infographic, but I do like this one. There literally is going to be data, like we think there's a lot of data now, we ain't seen nothing yet. And if you look in the top right corner, it says that there will be, in 2025, 463 exabytes of data will be collected every day. That's 463 million terabytes of data every day, okay? There's value in that data. Whether, you know, it seems like it's very challenging to get to, but that's where you want to be. Absolutely. So there's just data being collected everywhere, and things are going to change as a result. Okay, so once again, present state of data science. I think there's been a neat little inversion. In computing, basically it came out from the military / industrial complex, NASA as well, government. And then it came up in through industry, and then, you know, those of us who were around at the time got our nice little VIC-20s and Commodore 64s, and there were still playthings. And so computing kind of came through the industrial complex, whereas now data science really has come up through the consumer world, and it's an industry that's taken a little more time to get there. And in many sectors, as you know, I mean, this is trite, but Amazon was basically a bookseller until they got on data analytics and they transformed into this behemoth, to the extent now that AWS, Amazon Web Services, generates an equivalent profit to the entire retail arm of Amazon, even though I think their revenue is about 1/10 the size. But they're making a bucket load of money from AWS. Uber, people think that it transformed taxi driving. Actually, what it did do is transform dispatching. That's the game changer there. They don't care about the taxis. They're whoever they are over there. They're the ones who connect customers to the taxis. And that's where the game changer was there. And that's in the consumer space. Netflix, once again, I mean, they used to send out DVDs by mail until they figured out, hey, maybe streaming's a good idea. And that was the game changer, to the point that they're 1/3 of all internet traffic. So these things don't have to be like incredibly new ideas. Domino's, for God's sake, I mean, I order Domino's just because it's so convenient. You know, it's just so, and they monitor everything, and they, even to the extent that pizzas are not algorithmically generated, so to speak, but they've kind of decided how many slices of pepperoni should be on your pizza, so for maximum taste and also economic effect. There's 1,000 probably business models on your phone right now, right? It's everywhere. It's just that we don't quite understand it quite yet. So there's a wonderful book called Prediction Machines that came out in 2018 by 3 U of T economists. And I love how they kind of couched how data science, or they call it AI/ML. I'm just kind of all putting it in the same bucket for now. How they kind of bracketed in what does it mean from an economic perspective. Forget about the tech piece, from an economic perspective. And so I'll walk through some of the tech that we talked about earlier. Like the Jacquard Loom basically made weaving cheap. So before it cost a lot of money to make a tapestry, now it's way quicker. Oh, maybe you don't need so many weavers anymore, but you need somebody who can actually run that machine, and you need a tapestry designer, the person who puts together the punch cards. Electricity made light cheap, and as a result it opened up a world of opportunity, right, where you could actually study at night, for instance, not by candlelight, but you could do a lot. So it opened up educational opportunities, it opened up the computing revolution, it opened up everything. Digital computers made computation cheap. And that's what I was trying to show with the logarithmic tables, where that one page would represent like 20 years of human effort. Now it's literally a trivial thing on your phone. We don't need human computers anymore. Nobody does that. Although, I mean, I shouldn't go into this, but I will. The argument is that our entire educational system is still based on building human computers, right? You learn how to do every piece of algebra. You don't, like, is that necessary? I don't know. There's a big push now maybe that everybody should be data fluent and understand how to build a graph and how to wrangle large sets of numbers, as opposed to knowing how to do algebra to the nth degree, depending on your role. But we don't need human computers anymore. That's just not a thing, but you do need computer engineers for obvious reasons. And so what they argue in this book is that AI and ML makes predictions cheap. And that's a bit of a hard pill to swallow for a lot of technical professionals, including me, because we built our careers on making predictions. As a geophysicist, I'd take a whole bunch of data, I would build a map, and I would say, hey, you should drill here. Well, there might be a computer that can kind of do that. Whether it's doing a good job is a different story, but you should have somebody there to kind of do it. Whereas if I were to do something like that, it might take me 6 months or a year. Okay, that sounds fine, but the business cycles that we live in now, this actually happens in my shop. When we drill wells and we pick tops, so basically with well logs, you kind of say, okay, this is where the top of that formation, so the top of that formation. That's getting out of cycle with our entire drilling cycle. That's taking too long. There's ways of automating this stuff. And I would honestly say in about 5 years, the thought of picking a top manually will look hopelessly antiquated. It'll look like you're designing your tapestry by hand. Okay, and I know a computer won't do a great job, but if you have somebody overlooking it and training that algorithm and getting better at it, eventually it'll get to the point where, yeah, you can pick 1,000 different iterations and pick the best one, and that'll be good to go. So you don't need as many experts on how to do those things, but you need somebody who knows how to operate those algorithms. So how do we all fit into this space? And that's the challenging part here. I kind of look at it from two different perspectives. I call them the mechanics and the drivers. The mechanics are the people who actually will be the ones coding the algorithms, who have a very intense understanding of how they work. You still have to look at it from a problem perspective, and I think that's the key. Don't get caught up on this language or that language. If you need that tool for that problem, that's how to look at these things. So how will data science solve your problems? You have to get under the hood and understand how they work, and I'm trying to get there right now. And currently, the best way to do that is to speak the machine's language, which is coding. And that's challenging for a lot of people. It's still challenging for me. I try hard, but it takes a long time to get into a language, but that's just the way it works. But just as a really cool example here, this is a problem that you would never think of. The little graphic underneath is from a patent from Frito-Lay, in which they use both computer vision and acoustic sensing to measure the quality of potato chips along an assembly line. So you would think that's kind of really a pedestrian, yeah, like why really? Like this does not have to be, you don't have to send somebody to Mars, okay? It can be a very, very simple problem. A simple problem well solved will make a huge difference. In this case, I think they're saving something like $350,000 per assembly line over over 30 assembly lines in the US, and then they're going to roll it out to the rest of the world. And so it doesn't have to be, well, it will be a game changer, but it doesn't have to be something incredible. Something like this is just fine. So what happens if you don't feel like coding and getting into that? Because I know it is a lot of work. Tech changes every day. The tools change every day, and it's a lot of work to get involved. Well, I think just wrapping your head around data fluency, I think is key. As I showed earlier, there's going to be a ton of data out there. It's not going to slow down. Understanding how to wrap your head around that and how to make use of it, how to display it, how to store it, how to access it, those are key things that you need to understand. And statistics, that's the language of numbers. If you're doing quantitative work, if you're doing unstructured data, maybe it's natural language processing. There's all these different things, but find a problem that you're going to solve first, and then move in that direction. Don't just go around going, hey, I should learn this, 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 and this. I mean, I've been drinking from a fire hose for 3 years. It gets really tiring, right? So I just kind of try to focus on the problem and kind of go in that direction. And finally, for those of us who have technical careers, expert knowledge is absolutely critical. Domain knowledge is critical, but your biases may not be as useful as you once thought they were. When you look at big data sets, there are things in there that no human has ever seen or understood. And so as a result, you kind of have to be a little bit more open. Yeah, you should be coming in with your knowledge, but it may be telling you things that aren't immediately intuitive at all. And so as a result, you kind of have to check that at the door just a little bit. Okay, so this seems like a beautiful world. You know, everything's going to work out exactly as we planned. Well, there's going to be some uncertainties around this, right? And in the current world that we're in, things are uncertain. I don't know what algorithm will do this or what'll do that. This is all going to get itself worked out, you would think. And I think in about 5 or 10 years, we'll have a good sense of how these things do work, but by that time, it'll be like somebody knowing Excel. Like it's just expected and good for you. This is the opportunity to really do great stuff. Some of the uncertainties include acceleration. For instance, this is a graph of mobile and fixed landline telephone subscriptions. Year is on the x-axis, and then number, I think it's in the millions. Oh, measure per 100 people, sorry. So it's a standardized number along the y-axis. So you can see the blue line is the number of fixed telephone subscriptions. It's just a very simple linear accretion and over a number of years. But then as soon as the mobile telephone came in, you can see that the adoption just shot up over like 10 years, kind of coinciding more or less. Yeah, well, the inflection point is right around when the iPhone showed up. And so the idea is just to show that every tech that comes out will just be adopted and used more and more and more quickly. And I'm a little bit afraid to use a statistical term about the interaction effects when that happens. When this tech comes in with that tech, what does that look like? That's going to be dangerous. The stakes get higher. And I mean, a classic case in point is the meddling of the election, the US election in 2016. They were using techs like bots and all kinds of different technologies that nobody would have thought of to use in that circumstance. But boy, it made a real difference in the world, didn't it? The other uncertainty too is that data science is changing. Right now, it seems like, yeah, it's somebody hacking away in a corner. They'll set up Python or whatever and do your thing. Well, it's going to be a commodity soon, okay? In 5 or 10 years, it'll be something that any new grad coming up into a company will have those skills, and that'll just be the expectation. So to me, this is the ripe time to be involved with this. While things are uncertain and unclear, this is where you can make your mark. Right? It's just, I'm not telling you how to do it. You have to figure out how to do it. But there is an opportunity there. This is, sorry, Steve had a nice example of data science. This is my favorite one currently. This is considered the third wave data scientist. The first wave was the statistician, the PhD statistician, who went off and did their own thing and been doing it for decades. The second wave data scientist was the unicorn who came in and had all these skill sets all wrapped into one, but had difficulty actually producing things. And there have been a lot of articles stating that data science, like 80% of data science projects fail. And in a large measure was because of that. You had a unicorn who was able to do everything, but wasn't able to communicate it out, wasn't able to deploy it because you need IT, you need infrastructure for that. As Yogi showed last month, IT does matter. This I like because this shows that there are different parts to what a data scientist looks like, but the key part is the business mindset. Saying that I have this data, I can make something. As you saw in that video, there's a joke, that data scientists think that they can do everything, but actually delivering is a bit of an issue. No, you have to deliver. The actionable insight is what got me into this. I love that part of it. It is not a theoretical exercise. And yes, you need to know statistics and algorithms and software engineering. I've learned to truly appreciate that discipline. Boy, it matters, because even if you're working in an oil and gas company, if you're working as a data scientist, you have to develop a product, and you need to develop that so it's maintainable and reusable and reproducible, and that really matters. Soft skills, hopefully most of us have that here, so I'm sure you're fine with that, but it's that business mindset. So I think that's something that you can bring to the table that is not inherent. The other tools, you can learn those. So finally, the last thing that's been very helpful for me, and I think this is kind of a nice little paradigm for oil and gas as well. Oil and gas tends to operate in a more hierarchical environment where knowledge goes up and knowledge goes down. And it's a bit inefficient, and there's a lot of friction with that. And I think a more distributed model would be really quite nice. Been chatting, or I've seen a few examples now where we have these large organizations and they'll spin off a little startup that'll be weaponized to do this one specific thing. We haven't gone there yet in oil and gas, but I think that would be a much more useful system, a more distributed system. And I think learning is a similar thing. A lot of people in oil and gas have been kind of attuned to saying, okay, well, if I need to learn about this piece of software or that completion technique, I need to go spend $2,000 over 4 days to figure out how to do that. I just need to deepen my skills. I think data science is more about breadth, especially if you're a practicing data scientist. If you're one who's developing algorithms for autonomous driving, that's a different world. But if you want to be a practical data scientist, it's more about breadth than depth, to be honest. And I think you get that from a more distributed system. Hey, go talk to that engineer over there, or learn about how that biological or that algorithm that was developed in biostatistics might work within data science. These things transfer quite nicely. So that's been kind of my hedge. I learned from a lot of different places, and it's been extremely rewarding for me. So to sum up, here's some of the books I talked about. One Giant Leap was about the Apollo mission. The Algorithmic Leader by Mike Walsh just came out this year. And I thought it looked like it was pretty buzzword heavy, but it's actually really useful. It kind of states that, yeah, you should just kind of get used to knowing that you won't know everything that's going on in your company, but you just have to have some understanding of how these things might occur. And then, of course, prediction machines, the simple economics of artificial intelligence, really kind of help set the stage for me to understand of what AI truly is. It just from an economic perspective, not from a tech perspective. I'll cycle back to this in just a second here. And then my web references are 10. If you want any of these slides, just let me know. I can send them to you. And thank you very much.